On November 19, 1946, a routine administrative transport slipped into a high-altitude situation where small navigation errors stop being clerical and start being lethal. The aircraft involved was a Douglas C-53 Skytrooper, bearing the United States Army Air Force's serial number 42-68846. The mission was an administrative transport departing from Tulln Air Base near Vienna, bound ultimately for Pisa, with the day's routing intended to run via Munich and onward toward the western Mediterranean. The plan depended on precise adherence to magnetic headings and radio aids to keep the aircraft clear of the highest alpine terrain. Both were lost. This C-53D Skytrooper was the personnel transport take on the commercial DC-3 airframe, often grouped under the broader Dakota label in European accounts. While visually similar to the widespread C-47 Skytrain, the Skytrooper was configured primarily for carrying people rather than heavy freight. It lacked the reinforced cargo floor and the large double cargo door found on the utility models. Instead, it was fitted with troop and passenger seating and a cabin arrangement centered on personnel movement, not palletized cargo. On this flight, the cabin accommodated 8 passengers and 4 crew members. The manifest included high-ranking military personnel and civilian family members, including women and a child. They were dressed for a transfer in a heated cabin, not for exposure on an exposed ice shelf. What carried the Skytrooper into the Bernese Alps began as a simple failure of situational awareness. The aircraft encountered instrument meteorological conditions shortly after departure. Visibility dropped to 0. The crew was forced to rely on radio navigation and dead reckoning. In 1946, the navigational infrastructure in post-war Europe was fragmented. Radio beacons were often unreliable or shielded by the mountainous terrain. Without a distinct visual horizon, the pilots were subjected to the hazard of spatial disorientation. Spatial disorientation is a physiological disconnect between the vestibular system of the inner ear and the actual attitude of the aircraft. The human balance system relies on visual references to determine the vertical axis. In the absence of a horizon, the inner ear cannot distinguish between a coordinated bank and straight and level. Flight. If an aircraft enters a shallow turn, the centrifugal force generated by the turn aligns with gravity. The pilot feels as though he is sitting upright in a level plane, even as the wings are banked and the heading is changing. If the pilot trusts this physical sensation over the gyroscopic instruments, the deviation continues uncorrected. Without realizing it, the C-53 began sliding off its intended track. The crew believed they were tracking toward Munich on a diversion and then continuing toward the Marseille area, maintaining a safe separation from the high peaks. In reality, the aircraft had turned south and west, penetrating the perimeter of the Bernese Hochbergland. This region contains some of the highest and most rugged terrain in Switzerland. The drift placed the aircraft on a collision course with the WWII Glacier. At an altitude of 11,000 feet, the operational environment transitioned from navigable airspace to a chaotic weather system. The airframe was not equipped with weather radar or ground proximity warning systems. They had only a calculated position, and it was already miles wrong. The mountains below were obscured by cloud layers and driving snow. Outside air at that altitude was far below freezing, an exposure hazard waiting behind any breach of the hull. The crew maintained their cruising speed, unaware of the granite walls rising to meet them. They were not flying over the rolling foothills of the approach corridor. They were threading the needle between peaks that exceeded 12,000 feet. The navigation error had moved the aircraft into a geographic trap. There was no room to maneuver and no visual cue to warn of the impending terrain. The C-53 was a robust machine capable of absorbing significant punishment, but it was not designed to interact with a glacier at 170 miles per hour. As the flight continued into the afternoon, the discrepancy between the map and the terrain became absolute. The aircraft was no longer a transport vehicle moving between bases. It was a metal container carrying 12 people into a solid wall of ice and rock. The margin for error had been consumed by the initial drift. The result was an intercept vector into the Bernese Hochbergland, toward the WWII Glacier Basin. The passengers in the cabin had no warning of the deviation. They remained seated in the heated interior, separated from the -15-degree exterior by a thin layer of aluminum and insulation. By then, there was no clean exit. Momentum, weather, and terrain had already locked in the approach. The transition from flight to impact was governed by a number constraint, 174 miles per hour. This was the estimated airspeed of the C-53 when it encountered the final atmospheric boundary. The aircraft was not merely lost, it was being actively suppressed by the energy of the air mass surrounding the peaks. As the Skytrooper crossed the ridgeline of the Bernese Alps, it entered turbulent mountain air, including powerful downdrafts, conditions sometimes described as cat-a-bat-ik drainage flows in glaciated terrain. A cat-a-bat-ik wind is a gravity-driven drainage flow. On high glacial slopes, air in contact with ice can cool rapidly, become denser than the surrounding atmosphere, and spill downslope. When an aircraft flies into a descending column of air, it suffers an immediate performance penalty. The wing is generating lift relative to the air around it, but the air mass itself is sinking toward the terrain. The C-53 was caught in this downdraft. The pilots applied climb power, attempting to clear the rising terrain of the WWII Glacier. However, the rate of the downdraft exceeded the maximum climb performance of the laden transport. The aircraft was mechanically sound, but it lacked the thrust to overcome the sinking air mass. The altimeter unwound, forcing the hull toward the upslope of the glacier. Pilot Ralph Tate Jr. acquired visual contact with the terrain seconds before impact. The illusion collapsed as the white surface filled the windscreen. At this range, avoidance was impossible. The decision changed from collision avoidance to impact mitigation. Tate executed a flare, raising the nose to trade airspeed for lift, attempting to soften the contact angle. He committed the aircraft to a belly landing on the snowfield. The physics of the crash saved the occupants. If the aircraft had struck a rock face perpendicular to its flight path, the deceleration would have been instantaneous, resulting in a fatal structural collapse. Instead, the aircraft struck the deep snow of the glacier at a shallow angle. The snow acted as a fluid brake. It absorbed the kinetic energy of a transport weighing tens of thousands of pounds over hundreds of feet. The propellers churned into the ice and stopped. The engines were choked. The friction of the fuselage against the snow scrubbed off the velocity without shattering the cabin. The fuselage came to rest largely intact. The wings remained attached to the center section. The structural continuity of the tube prevented the passengers from being crushed or ejected. Inside the cabin, the violence of the deceleration threw occupants from their seats, leaving several people injured, including broken bones, but there were no fatalities. The Skytrooper had successfully converted its forward momentum into heat and displacement of the snowpack. The immediate threat shifted from impact trauma to thermal exposure. The silence that followed the crash was absolute. The aircraft was immobilized on a high-altitude ice shelf, surrounded by peaks that blocked radio line of sight. The ambient temperature outside the aluminum skin was well below freezing. The sun was setting, the heating system was dead. The 12 survivors were now static objects in an environment where human physiology begins to fail in minutes without protection. The aircraft had become a shelter, but its thin metal walls offered minimal insulation against the freezing night. The crash had been survived, but the trap had closed. For 5 days, the 12 survivors existed on the wrong side of a communication barrier. Finding the missing C-53 became an Alps-sized problem of angles, weather, and luck. In 1946, locating a crash site relied heavily on visual scanning, fragmentary reports, and radio bearings that could be distorted by mountainous terrain. Early messages placed the aircraft in the wrong area, and broken reception complicated the picture. The aircraft was effectively invisible, a white object buried in a white landscape, shielded by a ceiling of cloud. The operational clock was running against the thermal limit of the passengers. At 11,000 feet, the human body burns calories rapidly just to maintain core temperature. The food supplies on board were limited to chocolate rations and snow water. As the hours extended into days, the search area expanded to cover the French, Italian, and Swiss sectors of the Alps. The search teams were looking for a needle in a haystack, but the haystack was thousands of square miles of glaciated rock. Once the weather cleared enough for aerial reconnaissance to spot the anomaly on the glacier, the problem shifted from detection to access. The location was identified, but the vertical distance remained absolute. The crash site was situated on a high plateau guarded by sheer cliffs and crevasses. Conventional mountaineering columns would take days to ascend, carrying heavy medical equipment and sleds. The time frame required for a foot rescue exceeded the survival window of the injured passengers. The United States Army teams attempted to solve this mobility problem with mechanics. They brought tracked vehicles and heavy equipment into the region, including machines like the M29 Weasel, hoping to mechanize the approach. but the access to the WWII Glacier was steep, icy, and broken by crevasses. What worked on snowfields and roads proved impractical on a high alpine glacier. The concept was abandoned. This failure clarified the tactical situation. There was no road to the survivors. The mountaineers were too slow. The wreckage was trapped on an island in the sky, accessible only by air. However, the plateau was not an airfield. It was a sloping, uneven surface of deep snow, riddled with hidden fissures. A standard aircraft attempting to land would sink into the powder or shear off its landing gear on impact. The search phase had concluded with a grim realization. The survivors had been found, but the means to retrieve them did not exist in the standard inventory of the United States Army Air Forces. The solution would have to come from outside the established doctrine of heavy transport aviation. The geometry of the rescue was defined by a rigid limit, the relationship between runway length and lift generation. Standard military transport aircraft require thousands of feet of hard pavement to accelerate to flying speed or to decelerate to a stop. The WWII Glacier offered neither pavement nor distance. It was a short, sloping shelf of compressed snow, terminating in jagged rock and ice falls. Any aircraft attempting to touch the surface had to generate lift at speeds low enough to stop within the length of a football field. The United States Army Air Force's aircraft circling overhead were too fast and too heavy. They could drop supplies, but they could not touch the ice without becoming casualties themselves. The solution came from the Swiss Air Force, utilizing a machine designed for the extreme edges of the aerodynamic envelope. The aircraft was the Fieseler Fi-156, known universally as the Storch. Originally a German design for reconnaissance and liaison, the Storch was built to operate from unprepared fields, roads, and clearings. It appeared fragile, with long, spindly landing gear and a high-mounted wing, but its capability was defined by its ability to fly slowly without falling out of the sky. The Storch's short takeoff and landing performance came from high-lift hardware rather than speed. Fixed slats along the leading edge and large slotted flaps on the trailing edge. Together, they kept the wing working at steep angles of attack where other aircraft would have stalled. This architecture allowed the Storch to remain controllable at extremely low indicated airspeeds, down near 31 miles per hour in ideal conditions. That number was the key that unlocked the trap. It let the pilots approach the glacier slowly enough to match the limited braking friction of the snow. But the operation was complicated by density altitude. At 11,000 feet, the air is thinner. The engine produces less power, and while the wing still sees stall on the gauge, the true airspeed and ground speed rise. The margin shrinks in a way that the mountains do not forgive. Swiss pilots Victor Hook and Major Pichta Hitz fitted their aircraft with retractable skis. They approached the crash site, flying up the valley, fighting the erratic wind currents around the Alp peaks. The landing technique required absolute precision. They touched down flying uphill. The slope of the glacier worked in their favor, using gravity to help bleed off the aircraft's momentum. The skis distributed the weight of the light airframe, allowing it to float on the snowpack where wheels would have dug catastrophic trenches. The extraction process was a systematic shuttle service. The Storch was a small aircraft with a wingspan of 46 feet and a limited payload. It could not extract the group in a single lift. The operation required 9 separate rotation flights. The pilots had to land, keep the engine running to prevent the oil from congealing in the freezing cold, load the most critically injured survivors, and then execute a downhill takeoff. The takeoff procedure was a commitment to gravity. The pilots pointed the nose down the glacier and applied full power. The aircraft accelerated across the snow, using the decline to gain speed before the ice shelf dropped away into the abyss. Once the wings bit into the thin air, the aircraft banked away from the valley walls and descended to the safety of the valley floor. By the final rotation, the glacier shelf was empty of people. The operation demonstrated that aviation could function in environments previously considered closed to fixed wing traffic. It was not a miracle. It was the disciplined application of high-lift aerodynamics to a high-altitude constraint. With the departure of the final Storch flight, the operational objective shifted instantly. The rescue of the 12 occupants was a complete success. Every soul on the manifest had been transferred from the ice shelf to the valley floor. However, the Douglas C-53 remained on the glacier, a 26,000-pound aluminum structure, sitting intact on the snow. In a modern context, a recovery team might mobilize heavy lift helicopters to sling load the airframe off the mountain. In 1946, that vertical lift capability did not exist. The technology to remove the hardware was decades away. The decision to leave the aircraft on the glacier was dictated by more than physics. The Swiss pilots had pushed their light aircraft to the edge of safety to save human lives. Risking personnel for hardware on a crevassed glacier did not balance. And there was another pressure line: sovereignty and secrecy. The American side considered destroying the wreck to prevent sensitive equipment from falling into other hands. But Swiss authorities opposed blasting a foreign aircraft apart on their mountains. The outcome was blunt and final. The Douglas C-53 remained where it had come to rest, written off as a total loss and surrendered to the ice. The shelter that had kept them alive for 5 days was suddenly silent and unoccupied. The cabin, which had served as a shelter for 5 days, was now empty. The recovery team stripped what small portable items they could carry, but the engines, the avionics, and the airframe itself were surrendered to the terrain. This marked the start of the encapsulation process. On a glacier, encapsulation is not merely being covered by snow, it is a phased change of the surrounding medium. As new snow falls, the layers beneath are compressed by the weight above. The snowflakes lose their delicate structure, rounding into granular snow known as firn. As the pressure increases, the air pockets are squeezed out, and the firn fuses into solid glacial ice. The C-53 was not just buried, it was cemented into the fabric of the glacier. The aluminum skin, designed to hold pressurized air in, was now subjected to external static pressure. The ice filled the voids around the engines and the wings, locking every component in a rigid grip. This environment halted the standard decay of the materials. At these temperatures, chemical reactions slow to a crawl. The cold soak duration extended from hours to decades. The wreckage became a time capsule, preserved by the very forces that made its recovery impossible. For the families of the survivors, the event was over. The media cycle moved on. But for the mountain, the process was just beginning. The wreckage was now part of the glacier's internal mass. It would not rust in the traditional sense, as the low oxygen environment of the deep ice inhibited rapid corrosion. Instead, it would be subjected to the immense, crushing pressure of the moving ice stream. The C-53 had entered a long period of hibernation, locked away in a frozen vault that would keep it hidden from the world for more than 2 human generations. For 66 years, the WWII Glacier kept the C-53 out of sight, answering to melt and gravity rather than human timetables. It vanished into the white in 1946, and its coordinates became history, until the glacier's own motion made the wreckage relevant again. The mechanism that controlled this delay is glacial flow transport. A glacier is not a static block of ice, it is a high-viscosity fluid driven by gravity. The mass of the ice sheet is so great that it deforms under its own weight. It flows downhill, sliding over the bedrock and grinding against the valley walls. The WWII Glacier acts as a slow-motion conveyor belt. It captured the Skytrooper at the high-altitude crash site and began carrying it down the mountain. This transport process is destructive. As the ice moves, it cracks, folds, and shears. The aluminum fuselage, which had survived the initial impact intact, was subjected to immense crushing forces. The glacier dismantled the aircraft piece by piece, grinding the metal against the granite bed of the valley. In the summer of 2012, the glacier's flow finally delivered its first visible pieces into the lower melt zone. This region is known as the ablation zone. Here, at the lower altitude terminus of the glacier, the rate of melting exceeds the rate of new snowfall. As the surface ice recedes during the warm summer months, the objects trapped within the flow are exposed to the surface. 3 hikers crossing the glacier spotted a dark anomaly against the gray ice. It was a propeller. The blades were bent and scarred, but the hub remained recognizable. The Skytrooper had returned to the surface. This discovery triggered a new operational phase. The site was no longer a rescue zone, but an archaeological field. The debris field was located significantly downslope from the original coordinates of the crash. The ice had moved the wreckage miles from where Captain Tate had set it down. Over the next few years, more components emerged from the melt. Engine blocks, wing spars, and sections of the landing gear began to clutter the surface of the glacier. In 2018, the Swiss military launched a cleanup operation to remove the hazardous materials from the watershed. The environment had changed drastically since the era of the Fieseler Storch. The recovery team did not need to land on the ice. They utilized modern turbine helicopters capable of hovering at altitude and lifting heavy loads. The method was a vertical extraction. ground teams collected the scattered debris, netting the jagged metal and rigging it for sling load removal. The objective was not to reconstruct the aircraft but to clear the site. The glacier had thoroughly chewed the airframe. There was no intact fuselage to raise. The main cabin section was still believed to be buried somewhere in the ice stream, and modeling suggested it could re-emerge years later as the glacier continues to move and melt. It was not recovered during the cleanup. The operation retrieved approximately 2.4 tons of material. This included the heavy radial engines and the propeller that had signaled the location. The recovery closed the loop. In 1946, the mountain let the people go and kept the machine. In 2018, it gave the machine back, only after the ice had processed it into scrap. The C-53 did not fly out of the Alps, it flowed out of them, a reminder that glaciers can hide evidence for a lifetime, but ablation eventually returns it.